Okay. Well, hello and welcome. Let me talk a little bit about our exam. So we got an exam coming up 1 week from today, and I am still writing and just kind of going back and forth because my goal is for the average to be in the 80s, like 80, 85. That's kind of like the ideal exam difficulty for me is an exam average median score somewhere between 80 and 85. And I take on the burden myself to try to make sure the exam is around that difficulty. And if I um, and my philosophy is if I make it too easy and the exam average is like 195, okay, great. I'm not going to suddenly penalize you or anything. And then if I make it like too hard, like much harder than I thought, and the exam average is lower than that, then so let's say the exam average is like 70 and I wanted like a somewhere between 80 and 85. What I'll just do is I will just slide everybody up. I'll just add. So if the exam average is a 70, like if the median is a 70, then what I would do is I would just add 10 points to everybody's score. So the median becomes a 80, okay? And that means if somebody scored 100, they will go up to 110. And if somebody scored a 25, they'll go up to a 35, okay? So that's how I do quote unquote curving in on exams. It's not really curving, it's just kind of sliding, I would say. Okay, I'm going to just add points across the board. And again, the target for median is between 80 and 85. That's what I want for the median grade. And if it hits that, then no adjustments. Okay, so basically, if it's 80 or higher, I'm not going to make any adjustments. Okay, but if the exam median is below 80, then I'll just kind of add some points so that the class median becomes 80. All right. And so the hardest part for me as the teacher is putting myself in students' shoes and trying to guess how difficult the problem is for a student, right? That's the difficulty because like for me, I'm like, oh, this is easy. But then I understand, as students, you've seen this stuff for what, 7 weeks total in your life, okay? So I have to kind of think like, all right, you haven't established the vocabulary, you haven't established the fluency that I have, and so I'm trying to gauge how hard it is and exactly how many questions to put on the exam. This is kind of the other hard part because we're taking it in person here. You've got 50 minutes to do the exam, so I got to think like, what's the right number of questions to ask? And it's a double-edged sword. You put too many questions, then like students can't answer all the questions. Okay, but you put not enough questions, then it's like you get one question wrong, and like it drops. Each question now is weighted a lot more. So the way I'm putting it, okay, right, is this is the plan. And again, I'm still writing the questions and refining them. And I'm saying, okay, so this is what we're gonna have. We're gonna have multiple choice, and I'm aiming for around 25, give or take 3 questions. Okay, so somewhere around there for the total number of questions to ask. Okay, and then and here I have the content, and I'm still filling. I'm typing this up right now, but I have it in my head. Okay, so there's going to be a mix of code. A lot of it's going to be code, and then some conceptual stuff. Okay, so tidyverse things. We've got dplyr, select, filter, arrange, mutate, group by, summarize, left join, inner join. Okay. Then I've got pivot longer, pivot wider, okay, and ggplot stuff. ggplot. So pivot, okay. So for that, you'll need to know the AES, okay, and then I want you to be familiar with geom point. And for geom point, you should know X, Y, color. Okay. Geom point, you need to know geom call, okay, and you'll have X, Y, fill, and then position, and then facet rep. Okay, as far as tidyverse, and I'm gonna have this published. Okay, and then yeah, I don't know what I need to put in under mutate. So, and then I guess under mutate we'll have things like I'll put in string detect inside mutate there. Okay, and then outside of tidyverse, then we have a few kind of conceptual topics, right? So things like mean versus median, and then standard deviation, variance, IQR, hypothesis testing. So you'll have like a t-test and kind of p-values. Trying to think, am I missing anything? What did I put in here? Okay. All right, so kind of coding question format. So again, it's multiple choice. It will be kind of like example data set. And then I'll have, I provide a short, I provide a few lines of code. And then multiple choices of different possible outputs. And you select the correct output. The unfortunate thing is the exam is going to be like a whole bunch of pages, just because the format of these questions is like each question takes up like an entire page. That's like, because it's like, here's the code and like, here's one possible output, here's another possible output, here's another possible output. This is like, oh gosh. So the exam looks way longer than it actually is, but it's like one question per page type of thing, almost. Okay, so that's one possibility. Another possibility is example kind of starting data set, and then I provide the desired output, and you select the correct code to provide the output. Okay. And you'll have to kind of verify that. And that's pretty much going to be kind of the style for coding questions. And then the other kind of conceptual questions will just be like regular multiple choice. I don't think you'll need a calculator, but I don't know. If you're not confident, you can have a calculator about like, because I mean, some of the coding questions will be like, here's the data set, filter to this, filter to these rows, and then summarize and calculate the mean. And so you'll have to, like, in your brain, calculate the mean of maybe 4 numbers. But it'll be like 5, numbers less than 10. So it's like, can you calculate the mean of 4 numbers less than 10? Probably you can do it without a calculator. But if you like want to feel safe and be like, okay, I want, what is the mean of 8 and 7 and 6 or something, that's fine. No judgment here. Okay. Yeah. And, right now I'm just like kind of playing back and forth. It's really hard coming up with good multiple choice options. Like the correct answer, multiple choice is easy, the correct answer, but then like, okay, what are some not correct answers that aren't completely obvious that they're wrong? That's actually like, it's hard. So anyway, that is the format of the exam. Any questions? Yeah.
Yes, question. So what are we bringing?
Bring a pencil and an eraser. Yeah. I will provide the bubble in forms. Okay. So there will be
no blue book.
Yeah, you don't need a blue book. Yeah. No, if you need scratch work or just write on the exam. You don't bring scratch work or anything. Yeah. Yes. Yeah. Did you have a question?
Yeah, I was gonna. Are they all coding questions, or is that just one type?
They're not all coding questions. I'm thinking like 75% coding questions ish, something around there. Okay, and then 25% conceptual stuff based off of, and we'll say up through today's lecture as far as conceptual stuff goes.
And then for variance instead.
I don't need so much the formula as like the concept of like average squared distance from the mean. I mean, I guess that turns into a formula, but kind of the concept of that. Yeah. And then we talked about like ethics. I don't know. I don't know if I can write I don't know how to write a multiple choice question on ethics. So not to say it's not important. It's like if you don't put it on the exam, then the students are like, "Oh, it's not important." No, it is important. I just don't know how to write a multiple choice question on ethics, other than like, should you do the right thing? Yes or no. But again, like the question of like, what is the right thing to do in this scenario? I don't know if there's like an objective yes or no answer for ethics. Yeah. Yes.
Is it getting any questions dates?
So like I don't know. Like I don't have a no, I don't have dates questions, but if it's like filter by year, you would just say like year equals 2025 or something. I think that's okay, right? But I don't know. Yeah. Yeah, the question. Yeah. Okay. I guess maybe I should put that in conceptual questions here. Yeah. All right. Good point there. And today's content. So yeah, sampling, observational. Okay, I guess hypothesis testing, and then we have. Sorry. Thank you for pointing that out. Okay. We have sampling, data collection. So that's observational studies and experiments. Okay. And then today we have sampling distributions. Okay. Yeah. I might put a couple practice kind of coding questions, but again, the real hard part is coming up with multiple choice answers. So if I do release any questions, I'm not gonna come up with the multiple choice answers part. It'll just be like, here's an example data set and here's like a couple kind of things, but then like, I don't know, can you figure out what either the output would be or what code needs for the output? But yeah, sometimes like the difficult part of the question is that you look at your answer choices and you either feel like all of these are good answer choices, so that makes it hard, or all of these are bad answer choices, so that makes it hard, right? Like, I don't know if you took the SAT exam, but every time you read a question, it's like, okay, I have 4 possible, like, out of the 4 answer choices, like, 2 of them feel good, or out of the 4 possible, like, every single one feels terrible. And that's what kind of sometimes makes it hard. And I don't know if I am willing to do the mental work to kind of come up with good examples of those other than like the ones I have for the exam. So, okay. So that's what we've got lined up. Okay. All right, let's go ahead and take a look at our lecture for today, which is, where did it go? Statistical foundations. Okay, so we have to discuss a little bit about kind of sampling distributions. Okay, I'll talk about the normal distribution. We've already talked about sampling, and we'll also talk about the central limit theorem. Now, as far as the exam goes, you don't have to worry about like the specifics of like the normal table or something, but okay, but anyway, it is part of our lecture today. Okay, so the normal distribution looks like this. Okay, this is kind of what we call the bell curve. Okay, but because I guess you would put like a handle on here. It looks like a, I don't know, Christmas bell if you have a handle attached to the top here. Okay, but it's unimodal, it's symmetric. The idea is values near the middle of the distribution show up frequently. Values that are, as you go above average, it's less frequent. As you go below average, it becomes less frequent. And then when you're like really far above average, it's like super less frequent. Really far below average is also very infrequently. And if you color the area underneath here, if you shade this in, the total area is always equal to 1. And that's kind of a property of all probability distributions, because the probability of something happening is always going to be 1. And that's what the probability distribution represents. It basically represents, this is, along the x-axis is basically the values that could happen, and the height of it represents how often it happens relative to the other values. So this happens most frequently relative to everything else, and this happens much less frequently relative to everything else. Okay. So a lot of times we'll talk about probabilities and things like that, and if we're referring to the normal distribution, okay, kind of our starting point is the standard normal distribution. The standard normal distribution has a mean of 0 and a standard deviation of 1. The symbol for mean, when we're talking about a probability distribution, is this symbol mu, okay? And then the symbol for the standard deviation is this symbol sigma. Versus when you're talking about a sample, we often use x bar as the mean, and we often use S for a sample. But when we're talking about a probability distribution, then we have mu and sigma. This is just kind of like, we're just touching on some of these things. And as you take more statistics courses, like if you take Stats 100B or Math 170S or whatever, then you'll cover all of this in a lot more detail, okay? Another weird thing is that when you have a continuous distribution, the probability of observing any one exact value is 0, okay? It's kind of like, if you pick a random number on the number line, okay, and you write out that number to infinity decimal places, okay, what is the probability that the number you selected on the number line is exactly equal to pi, where it matches to infinity decimal places, okay? And the probability of that happening is 0, okay? There is a location on the number line that corresponds to pi exactly with all million or infinity decimal places, but the probability that you would just randomly select that is 0, okay? And it's actually true for any other point on the number line, okay? You might think about, okay, well, what about like 0? That's got to be easy, right? But if you think about like 0 matching exactly to, with 0 decimal places, infinity zeros after the decimal place, okay? And if I just say, hey, pick a random spot on the number line, what's the probability you're going to get it exactly at 0.000 with infinity zeros? Also 0, right? It's the probability of basically every number on the number line there kind of has, the probability of that happening is 0. And so when we look at probabilities on a continuous distribution like the normal distribution, the probability that z is less than 0 is exactly the same as the probability of z less than or equal to 0, okay? Because the probability of getting any one exact value is 0. So we always have to kind of talk about like a range, like what's the probability you're going to get something between 0 and 1, things like that, okay? So, all right, so simple enough. What's the probability that z is going to be less than 0? That's going to be 1/2, because if you shade the area to the left of 0, that corresponds to 0, area less than 0, and that's going to be, the area is 1/2, okay? So 0.5 due to symmetry. What about the probability that you get something greater than 0? 1/2, okay? That's easy, all right? And you just take the area subtract off the area to the left, okay? The area to the right, 1/2, okay? Easy enough. We've talked about the empirical rule, okay? And that these numbers, 68, 95, 99, 7, when we talked about like which values are extreme and how unusual, we talked about z-scores. We said, how far is something from the mean measured in standard deviations, okay? That comes from the normal distribution. We've got, if you go 1 standard deviation, that's around 2/3, 68%. If you go out 2 standard deviations, you get around 95%. And if you go to 3 standard deviations, and so I don't know if you can see, but this is 3 standard deviations, this tiny little sliver and this tiny little sliver corresponds to basically 0.3%, okay? And that is, just a tiny bit. But basically you get almost everything, 99.7% between 3 and -3, okay? So if you want to calculate something and you have a z-score, you can use R to get it. So if I say, all right, let's go to 0.42, right? So here's 0, and we're not going out to exactly 1 or 2, but if I just go a little bit and I say, hey, how much have I shaded in here? Okay, how much is to the left of 0.42? All right, we can see like, all right, it's a little more than half, but exactly how much? Okay. In R, you type in P norm. P norm is basically probabilities associated with the normal distribution. It's cumulative probabilities, and we'd say the area to the left of that is 0.6627. Okay, so if you do P norm 0, you would get 0.5. P norm 0.42 gives us 0.6627, 275 says 6628, something like that, okay? P norm always gives you the area to the left. If you want the area to the right, what do? We just do 1 minus that, okay? So I would do 1 minus P norm 0.42. The area to the right is 0.3372. There is an option. You can do P norm 0.42 and then lower tail equals false, and then it gives you the upper tail, the right-hand side, and you get the same 0.3372, okay? But probably the easier is just to do 1 minus P norm 0.42. The normal distribution is symmetric. So if we say how much is to the left of negative 1.04, that's going to be equal to how much is to the right of positive 1.04, okay? Because it's symmetric. So I don't know. I don't have a picture corresponding to that, okay? But because it's symmetric, you can imagine on the normal distribution, if I go back to any of these things, right? If I say how much is to the left of, say, negative 2, it's going to be the same as the area to the right of positive 2. And so that holds up for basically any number. The area to the left of some number z is going to be equal to the area to the right of the positive of that number, or the inverse of the number. Yeah, question. Oh, the round 4, this is just to round it off to 4 decimal places. So it's easier to kind of visualize because I don't know, how many decimal places is this? 7 decimal places? It's fine. Yeah, the round 4 is just, it's just for visual, just to make it a little easier. In like a traditional stats class, like if any of you took AP stats or something, I don't know if you ever had to look up values in a table in the back of the book. Values in the table in the back of the book are generally rounded off to 4 decimal places or something. Okay, so this would match that if you looked it up. Okay, and then if you want to generalize, so that's the z distribution, and so we could say let's do it for something that's the normal distribution but applied to the real world. Okay, and so heights of adult males in the United States approximately normal. Okay. We call this the normal distribution because it shows up in a lot of places. It shows up in a lot of places where it's like something is the cumulative effect of stuff added together. So anyway, we'll say in the US, approximately normal, where the mean is 69.5 inches, standard deviation approximately 3 inches, okay? And shorthand, you would say normal distribution, mu equals 69.5, sigma equals 3. Height follows that distribution. And we could say what proportion of adult men in the US are shorter than 72 inches. And so our diagram looks something like this. 69.5 goes in the middle. We end up a little bit higher than that, 72, and we say what proportion is shorter than 72, okay? So what we do is we measure the z-score, okay? And we talked about z-scores, which is how many standard deviations an observation is from the mean, the distance from the mean expressed in standard deviations. So we are 2.5 inches above the mean at 72. 72 is 2.5 inches above the mean of 69.5. So that's just under 1 whole standard deviation. 1 whole standard deviation is 3 inches, and we're 2.5 inches, so not quite 1 full standard deviation, 0.833. And so I would take this number, and I would plug that into P norm. If I put in 0.8333, it says 0.7976, so just around 80%, okay? Just around 80% of heights in the US, if these numbers are assumed to be true, are under 6 feet tall, okay? Whoa, something just happened. Okay. You could also call P norm directly. You don't have to, like here we calculated the z-score and we got 0.833, and we plugged it in, we got this number, 0.7976. You can also call it directly in R using P norm 72, mean 69.5, standard deviation 3, and it gives you the same thing, 0.7976, okay? And so same kind of thing, right? And then if you want the opposite, okay, so let's say we want to find like the 98th percentile or something like that. So if you want to kind of work in the opposite direction, then you would use something called Q norm, okay? So this is, so for example, let's say you're at the hat factory and you want to kind of make sure your hat can be adjusted to fit most people's heads, okay? But you're also like, well, some people have really big heads and we're not going to worry about fitting every single person because then you have to, then you have to accommodate too many things. So you're going to say, let's just make sure we can accommodate up to the 98th percentile. So if somebody is in the top 2%, so basically in a random selection of 50 people, our hats should accommodate 49 of them. And sorry to that 50th person out there with the biggest head, our hat's not going to fit your head. Okay? So how big do we want to go? Okay? So we want to figure out like what is this cutoff so that we get 98% to the left and only 2% to the right. Okay? I made up some numbers. I don't actually know what's true. Okay? I don't know what the average head circumference is, and I don't know what the standard deviation of head circumference is. But let's just pretend it's these numbers. Okay? How do we go from these numbers where we say, okay, the mean is 23 and the standard deviation is 0.8, and what I want to know is like, what is the mystery number here so that I get 98% to the left? Okay? We use the inverse function. So it's P norm gives you give me the measurement and I'll give you the probability. Q norm, and it's just because Q comes after P, all right? There's no like, I guess Q can stand for quantile, but basically Q norm is you give me the probability, I give you the measurement, okay? So P is you give me the measurement, I'll give you the probability. Q is I give you you give me the probability and the computer gives us the measurement. So here we say, okay, the Z that gives me 98% I call Q norm, 0.98. That corresponds to a Z score of 2.0537. Okay, and then remember the Z score is X minus mu divided by sigma. So if we had to solve for X using this, if we solve for X and multiply both sides by sigma and add mu, and so I would get mu plus Z times sigma. Okay, so then my mu is 23, my Z is 2.0537, my sigma is 0.8, and if I do that, I get 24.643, okay? 24.64, that would be the 98th percentile for head circumferences here, okay? So that's Q norm, and again, you can do it directly just by typing in Q norm 0.98, mean 23, standard deviation 0.8, and you get the same answer also, 24.643. Okay, and you have that. Okay. If you want to say, all right, let's just accommodate the middle 96% of people, so we're going to cut off the top 2% and the bottom 2%. Okay, you can do the same thing and say, all right, what is the head size of the bottom 2%? So here I'm doing Q norm 0.02, mean 23, standard deviation 0.8, and we get 21.357. So if you want to accommodate the middle 96% of head sizes, so again, in a room of 50 people, biggest head, we're not going to accommodate smallest person's head. That sounds so mean to say. Is 21.357, and we'll just make sure our hats can adjust between these two things. And I just made up the numbers, but I think that's approximately right, because if you look at like the headband with like the little pegs that you can adjust this hat size, I think the amount you can adjust is around 3.5 inches. So something around there, okay? Okay, so hats should accommodate something like that. All right, so that's normal distribution. Oh, I totally forgot. Give me a second. Okay, let me go ahead and give you your first two answers, E and B. E and B are your first two answers. E and B. Okay, we've talked about this stuff, populations and samples. You have a research question. You know, if we could afford it, if we had unlimited time and energy and resources, we would interview every single person in the population. Okay, but that's not possible because the population has too many people. So we subset. We take a small selection from the population. We're hoping our sample is representative of the population, and we get the information from our sample, and then we try to make inferences or conclusions about the population based on our sample. Okay. So if you have some kind of property of the population, that's called a parameter, and you have summary values from your from your sample, those are called statistics. Okay. So, you know, if you're trying to estimate, so basically, we're trying to estimate parameters based off of sample statistics. Okay, so we observe our sample, we calculate a statistic, and based off of that, we're trying to make guesses or conclusions about the parameters. So the parameter might be like, what is the true average height of all adult women? And then your sample is like, okay, we surveyed 100 people, and we get the average height of that. And we're hoping our sample average looks like the population average, okay? And you can do something like a political poll or whatever, right? Okay, so these are just examples. You surveyed 800 likely voters, that's your sample. Your statistic might be 44% support candidate A, that's your sample proportion. And so based on that, we're gonna try to guess, okay, what the actual proportion on election day is gonna be. And so maybe around 44%, maybe a little higher, maybe a little lower, okay? I don't know, similar stuff, okay? Here, you can do some kind of medication study. You have your sample values, and we're hoping that what we see in our sample can be used to estimate what's actually happening in the population. So you might say like, okay, some people got medication, some people got placebo. What we want to see is the medication reducing blood pressure. And so in our sample, that's what we see. We see those on the medication, their blood pressure is 10 points lower than those on placebo. And so now the question is, does that mean in the population would also get 10 points lower? Or the question in the back of our minds is, could it just be a random fluke? Could it just be a random fluke? All right. So all of these things, we have different symbols just so that we can keep track of whether we're talking about a sample value or a population value. Don't worry about memorizing this, okay, for the exam or anything like that. You don't have to memorize this. You will become familiar with it over time. As you get exposed to this, it feels like there's a whole bunch of stuff, okay? The general guide, okay, overall, usually we have Latin letters for sample statistics, and we have Greek letters for population parameters. That's generally the case, with the exception of proportions. But like for the mean, we'll have like Y bar or X bar. We have Greek letter mu. Okay, standard deviation S, Greek letter sigma. Correlation, Latin letter R. Corresponding Greek letter is rho. It looks like a P, but it's a rho. Okay, we have beta B for the slope, and it's beta 1 in the population, things like that. Okay. Then the exception again is proportion. We like to use P, and for the sample it's P hat. Okay, but most of the time it's Latin letters, our regular old alphabet that we use day to day, and then Greek letters for populations. Okay, we talked about sampling already, but here's just another slide on it, and we want all of this. Okay, let me talk about sampling distributions, and I'll probably have to continue this on Friday. The idea here is that when you take a random sample and you calculate something like the mean of your sample, okay, because it's a random sample, your mean is going to be different from one sample to the next, right? Like if you take a random sample of people, I take a random sample of random people, another student takes a random sample of people, and we say, even if we're like trying to measure the same thing, like how much cash is in your wallet, okay? If we ask the same question, but we're surveying different people, we're going to get different averages, okay? And it's just because it's a property of just the random sampling. And so you could ask something like, here is just a made-up thing. I don't know. Exam scores are rarely normally distributed, but maybe there's some exam that's normally distributed. The mean is 75. Standard deviation is 10. One person surveys 20 random people, calculates the average of those 20 people, they get a 73.5. Somebody else gets an average of 20 people, they get 76.1. Somebody else takes 20 people, they get 74.9. Okay? All of these things, like if you don't know that the population is 75, you could use this as kind of a way to draw inferences about the population mean, right? Because this is the idea. We usually only get to see a sample. Based on what we see in the sample, we're trying to draw inferences about the population, okay? So each of these things estimate the true value of the population, but they differ from one sample to another. And so the question is, how much do they differ? Are certain values or ranges of values going to be more common and things like that? And that gives us a sampling distribution, okay? Here's just another example, okay? So let's say we have a population. In the population, the true value is 16, okay? And there's a standard deviation of 5. And we're going to draw random samples of 5 values. So when you do that, what kind of numbers are you expecting? If I draw 5 numbers, I would expect my mean to be kind of close to 16, okay? Some values of y bar are going to be more probable than others, okay? And so here I'm going to say, what's the probability that I get a mean of around 15? So around here, this, you can just be like plus or minus, I don't know, 0.1. So like 14.9 to 15.1, because again, the probability of getting exactly 15 is 0, okay? But we could say, all right, values between 14.9 and 15.1. Or 13.9 and 14.1 and 11.9 and 12.1 or something like that, right? And so if you think if the original population has a mean of 16, could I get a sample where the mean is around 15? That sounds like it's pretty likely to happen, okay? What about a sample where the mean is only 14, okay? We can imagine that happening, but it's certainly going to happen less than the ones that are around 15, okay? What about a mean what about a sample where the mean is only 12? Okay, and now that starts to feel really unlikely, right? So if the distribution is centered at 16, standard deviation of 5, basically we're saying what? 2/3 are between 11 and 21, one standard deviation of up and down, and then 95% are between 2 standard deviations down and 2 standard deviations of up, so between 6 and 26, and then almost 100% would be between 1 and 31, okay? There's like 3 in 1,000 outside of that range. But basically 95% are between 11 and 26, okay? So could you get a random sample of 5 values where the average is around 12? And that feels pretty unlikely to happen. What about a random sample where the average is 8? Okay, and that feels really unlikely. And then what about a sample where the average is only 3? And again, that just feels like that just shouldn't ever happen, okay? And basically, we have this intuitive sense that the farther a sample mean is from the true average of 16, we feel like that should happen less and less and less. Okay. Now we know things are random, so weird things do happen, but the farther we get away from the true value, that's less and less and less. Okay, that's our intuitive sense. And indeed, when we do math for the sampling distribution, that's what it shows. Okay, so the sampling distribution is the formal definition, not a formal definition, but like kind of a definition appropriate to put on the slide here, okay, is the probability distribution of the sample statistic, like y bar or p hat or whatever, if we were to draw all possible samples of a given size n from a population. It's kind of a mouthful. But it basically tells us when you calculate a statistic like y bar or p hat or whatever it is you're looking at, what kind of values can you get? Which values are more likely? Which values are less likely, right? So, values of around 15, those seem likely. Values around 3 seem really unlikely, okay? And that's basically what the sampling distribution is going to show, okay? If we're talking about the sampling distribution of y bar, we call this the sampling distribution of the sample mean, or the sampling distribution of y bar. And it's just the sampling distribution of whatever statistic you're calculating. So to illustrate this, we can simulate this, and there's like a little application that I'm going to click, and basically we're going to kind of build up the sampling distribution in this simulated fashion. And this is all the time we have for today. But let me just start by here. We're going to start with the population. I'm going to just draw a random sample of 5. I'm going to calculate the statistic, the mean of that sample of 5, and then I'm going to make a histogram based on that. So let me click and open this up. I'll click begin here, and let's magnify here. So this is the population. The population is defined with a mean of 16, standard deviation of 5. And let me click animated. So here I'm taking 5 random values, and I say, okay, what is the average of these 5 values? And I get a plot right there. Okay. All right, so we'll continue this. Okay, we'll continue this on Friday. But we'll go ahead and wrap things up here. And let me give you your last view quiz answer. The letter C. C as in cat. C as in cat. Okay. We will end here. All right. See you guys later.